Okay.
Hi.
Hello. How's it going?
Good. Hello, everyone. All our marvelous attendees. Welcome to the first Java Champions Conference we ever organize. I do hope we'll do tons of others.
Yeah, that'll be good.
And so this is the afternoon of the first day. So don't miss all the other presentations. We have 3 more days afterwards. Today, so right now, let's talk about now. We have Richard Warburton with us, which is a performance expert and leading his own company doing that. He has one of the coolest English names I know. I do love your name. I told you that. Warburton, it sounds so powerful in English. It's amazing. A long time ago, he did something I found really interesting. I think it was the first, we call that unbiased profiler, called the honest profiler. You might talk what is an unbiased, about what is an unbiased profiler. I won't explain, but so I'll let him do it if he wants, or just check on the web. Meanwhile, today he's talking about continuous profiling in production, and I'll let you with him as of now. Hello, Richard.
Great. Hi. Thank you very much.
Now, do we have, okay, well, I need to push your your slide to do it correctly, and I need to remove my face from there
now. Excellent. Yes. And maybe make the slides a bit bigger as well. Great. So yes, this talk is called Continuous Profiling in Production, What, Why, and How. And as I already said, I'm Richard, and I run a company called Opsian that does have a continuous profiling tool, but this isn't really a talk about the tool. It's a talk about kind of methodology and why you might want to do this kind of stuff and what the pitfalls are for doing profiling in production. So firstly, we're going to have a look at why performance tooling matters and what kind of questions you can answer with production performance tools. Then we're going to look at the difference between development and production environments in terms of measurement, in terms of biases. We're going to have a look at the different ways you can measure data in production, different monitoring and profiling approaches. And then we're going to narrow down in on continuous profiling and see how it can be done really accurately and with really, really low overhead in production. So when you've got an application and you take it live into a production setting, there's a kind of range of different problems that you can encounter as you're going along. And the first type of problems might be your known knowns. Now, I'm talking here in terms of performance problems, but it kind of happens in terms of lots of different things. So known knowns are kind of known performance aspects that you have control over. So like you know ahead of time before you deploy anything into production that it's going to be faster to get data out of main memory than on disk. So you know if you want to have access to your data really rapidly, you want to try and keep it in memory rather than writing things on disk. This is something you can reason about ahead of time. It's the kind of thing you can architecturally consider and analyze ahead of time. Then there are your known unknowns. So known unknowns are kind of problems where you know it might be a problem, but you don't know what the exact right solution is. So these are the kind of things where you can build a system and then you can do things like run performance tests on your system to understand the answers to these things. Like, for example, maybe you decided that architecturally you were going to put a cache at some point in your system, but you weren't sure what the right configuration options were for that cache. So you could tweak that cache, do some performance testing, and find out the right kind of things. But for me, the biggest class of problems that software developers hit, especially as pertains to performance with their Java application, are the unknown unknowns. So these are things which not only do you not know the solutions to them ahead of time, but also you didn't necessarily know they were going to be a problem. They can sometimes be really, really simple things, which if you had thought about ahead of time, they'd be really easy to fix. So for example, I know people who've put really nice, smart, clever parallel algorithms into production and not realize that their nice, clever algorithm was being slowed down to one single thread or only a few threads due to contention on a log4j component within their system or things like that. They're things which you wouldn't necessarily think of, not necessarily complicated things, but things where you need to use production-oriented performance tools in order to understand those kind of problems and in order to gain insight into what your system's really doing. So it's really important to think about the unknown unknowns when you're taking an app and putting it into production, not assume you can reason about everything up front, even if you know your architecture well and you know your performance and your hardware pretty well. Okay, so having said that we want to have tooling that lets us measure our unknown unknowns, our aspects of our software that we can't reason about, well, what about development? So normally when we think about testing software, we think about things like JUnit, functional tests. And those functional tests we often run inside a development environment, right? Like I can start up IntelliJ, I can run a JUnit test within the IDE, I can get immediate quick feedback. But that's often a really bad idea to be doing from a performance problem type perspective. So performance testing fits into a different kind of category or a different approach than regular functional testing. Why don't we want a performance test in a development environment? Well, firstly, there's the question of representativeness of hardware, unrepresentative hardware. Many people do development on a laptop or maybe a desktop that they have in their home office these days during the COVID pandemic, or their work office when things go back to normal perhaps, and they deploy their software often onto some kind of server class machine, maybe some big beefy server in a data somewhere, maybe to a more modern cloud environment. When people look at the unrepresentativeness of hardware, they often think, well, look, if my laptop or my desktop is slower than the hardware that I'm running things on in production, then I'll be okay. But that's not really the right way to look at things for two reasons. Firstly, a lot of modern cloud hardware deployments are often run on quite slow hardware, and your development environment might be faster than it, just in pure CPU terms. You might also find that the ratio of performance between different components within your hardware is different to your production system. So maybe you've updated your laptop recently and it's got a really nice fast NVMe disk, whereas your production system, even if it's got a faster CPU with more cores, might still be running on an older SSD or even a hard disk perhaps. So the bottlenecks can shift between components there as to whether you've got slower or faster components in different parts. And finally, the issue of many core servers that have 32, 64 or more cores means that sometimes you can get concurrency problems, lock contention issues that you'll see in production that you wouldn't see in a desktop or laptop class hardware, where maybe you only got 4 or 8 cores, and being efficient with the way you use those cores isn't necessarily the biggest bottleneck. So unrepresentative hardware pushes bottlenecks different places, and that means you waste time solving the wrong kind of problems. Same thing with software. Many people do their development on Mac OS, many people do their development on Windows and deploy to production Linux systems. Obviously, there might be a few people who also develop on Linux and deploy to Windows, less common scenario, but you have to consider that the different versions of your software that you're using can have big impacts on the performance of those different systems. So different operating system version, different JVM version, different versions of lots of things. Even if you have a consistent environment between, say, Windows in development, Windows in production, or Linux in development, Linux in production, you can find that small security patch updates cause big performance changes. Back in May 2018, Microsoft released a regular patch Tuesday security update for Windows that tanked UDP throughput on certain benchmarks that I and people I knew were running at the time by 40%. 40% throughput tanking. That's huge. And that's just a security patch. I mean, that was admittedly in respect to the kind of Spectre meltdown problems and the mitigations around that. But it just goes to show you how big the difference can be between even minor versions of the same operating system, let alone between different operating systems that have different schedulers, network stacks, all sorts of things. Again, pushes the bottleneck to different places, gets you focused on the wrong performance problem. Then there's the unrepresentative workload problem. I think this is the most difficult problem to solve in terms of performance testing and ahead of time performance analysis before you put code into production. And that's because it's really, really difficult to produce performance tests that are realistic of what your production system is doing. It might be that the performance test you're using uses the wrong number of users, that you only get performance problems that you experience when you have lots of concurrent users on a site. It might be that the page load distribution that people use in production, so people hit different URLs that cause different performance problems compared to your performance test. It might be the way that you hit different caches within your system, different access patterns to database, the order in which you visit certain pages, all sorts of different things that could have different varying stresses between writing a performance test in a development environment or a QA environment versus a production workload. And then there's the fact that as your software changes, as its UI changes, as the pattern of behavior of your customers change, so does that workload that they perform. You write some performance tests which are good one day, then maybe you redesign your site or you add new features to your site. That changes the way people use it. That changes the way people use your software. It means you have to maintain that performance test as you maintain your software as well. So it's not just getting a good set of performance tests that you would need in order to accurately analyze your software ahead of time. It's maintaining them. And oftentimes the cost to you to maintain those things can mean that even if you can get this right, it may not be worth it for your business compared to actually just looking at what the production system is doing. Then there is the characteristic of the JVM itself. So JVMs do adaptive optimization. What that means is that they look at the behavior of a piece of software. So they look at what methods are being called within your system and adaptively optimize, inline, compile based upon methods that they consider hot within your system. That's to say, actively used and called lots of times. Now, sometimes your production system can optimize differently from a development environment because it might warm itself up differently to a load test. One of the most interesting examples I've seen of this is a system that had a clustering system and it had a strong leader and followers for that leader in a kind of consensus algorithm. And everything worked quite well, quite effectively, with the business logic being operated on the leader, and the followers were keeping the state up to date in their system, but they weren't executing the business logic. Then a net split happened. The leader flipped over to a different follower, and that became the new leader within this system. And the new leader suddenly had a massive drop-off in throughput compared to the old leader that it saw. And that drop-off in throughput was basically because Hotspot had adaptively optimized the followers. So it had looked at all the paths in the code base, and there were all cases where basically the kind of follower stubs with no business logic were being executed, and Hotspot had optimized for that follower case. And then it had to back out and re-optimize when they became the new leader. So there was a big drop-off in throughput when the leader switched to a different node. So that's a different example of the kind of thing that can result in very weird behavior that's JVM specific. And that's also a case where it will work differently in production to a development environment. Sometimes you have to say, look, I'm an expert software developer. Normally I know what I'm doing, but sometimes I just have to sit back and say, I have no idea what I'm doing. This dog looks cool, but you don't want to be the dog. You say that I say that because sometimes you have to just accept that you're not going to know everything about how your system behaves. You're not going to be able to analyze everything in your development environment. You're not going to be able to get everything right. You need to stand back and use a more resilient way of measuring things, which is measuring what's actually going on in the production system, in the real world, on the real data, on the real workload. And when we come to do that, when we come to say, look, I need to measure my production system rather than my performance test in my development environment, we need to think about what data we can measure from the production system. Because if you're running things like a profiler or a measurement tool in a development environment, it may not matter that much how much you slow down your system. But when you're trying to measure a production system, you need to make sure that's really efficient and really low overhead. The first thing that people often jump into when they're trying to measure production systems are metrics. Sometimes it could be system metrics, ambient metrics, passive metrics. Metrics are all basically numerical measures that you've pre-configured within your system. So they could be things like how much CPU is being used within a 1 second interval. How much of that CPU time is spent in user space, in kernel, doing I/O, simple things like that you could just get from VMstat. It could also be other types of metrics. For example, page load times, distributions of latency histograms and things like that for page load times. Metrics are a really useful feature that you can get out of your production system. They're really useful in the sense they help you narrow problems down. They help you analyze what component within your system a problem might be arising in. And they're, as well as being effective, or they can be effective, they can often be very cheap to collect. When I say cheap to collect, I don't just mean cheap to collect in terms of the dollar or the pound or the euro cost for gathering that metric. I mean cheap in the sense of being very, very low overhead. They aren't going to slow your system down very much when you're measuring a metric. But there is a big problem with metrics, and that is that when people gather metrics, they tend to put them on a big dashboard, try and collect as many of them as they possibly can. And then you get these, when an actual performance problem comes in, you get one of these murder mystery weekend style scenarios, like an Hercule Poirot novel or something like that. You know, at the end of those books, Poirot, he always goes around and he looks and he accuses every single character in the novel. It's your fault, it's your fault, it's your fault. And it's always the last person to be accused who's inevitably the murderer or whatever it is in the story. And that can often be the case with metrics. If you just look at these metrics and you go through them one by one, if you've got a lot of metrics, you can be searching for a needle in a haystack. And you go around trying to find which of these metrics is the key pointer to what's your problem, and you don't necessarily know which one it is. And sometimes it can lead you to useful information like we're using too much CPU, but it doesn't tell you where in your code base or where in your system you need to fix the problem. So metrics, very useful, very effective, but you get this murder mystery weekend problem that sounds fun, but actually in reality isn't. So the next thing we're going to have a look at is logging. So logging here, just recording a sequence of events that are emitted by the system that you're monitoring. And you can get different forms of logging. You can get just regular Java logging, log4j, left4j, logback, things like that. So those are arbitrary events that you write by yourself within your code base to emit. And you can often get systems nowadays that aggregate and analyze those logs. You can also get specific logs for subsystems within your system, like garbage collection events and things like that. Logging can often be really, really fine, detailed information and can often be very useful for understanding the system. But there are two big problems. Firstly, it's very expensive. The more information that you emit by that system that you're measuring, the more you have to analyze it and the more the overhead is for storing and aggregating and searching that data. Secondly, if you're manually instrumenting things in your system to emit logging entries, that's a very time-consuming process. I know organizations that have literally teams of people who do nothing but add more observability or monitoring to their system by adding more and more log events. And that's a cost that gets borne by your business. And in the case of things which are automatic logging, like GC events, they can often be, GC logs can be a very useful view on what the system is doing, but often only a view of the very one part of that system, of the GC subsystem, and not the whole system. So logging, again, potentially useful, but pros and cons to it. Then there's coarse-grained instrumentation. So most APM tools, application performance monitoring tools, use this general approach. So they add some instrumentation code to their system. So for example, measure the time when you enter and leave a method and subtract one from the other to find out how long you spent within that method. Coarse-grained instrumentation can give you very, very detailed and very, very fine-grained view as to what your system is doing, actionable insights, so things that tell you what's going on. But the problem is that the more you add instrumentation to your system, the slower that results in your system becoming. So the more overhead you're bearing. And when you're trying to speed your system up, you don't want to have lots and lots of overhead in terms of your production monitoring tooling. But it can still be useful for things like how much time did you spend inside the control layer of your web app, or how much time did you spend performing SQL queries, things like that. Then there's profiling. So some developers do profiling today in their development environment. Not that many, though. An increasing number do production profiling as well. So that's profiling of an actual production system. Profiling is a very general approach. That's just about allocating resources to what is using the resource. So what methods used up CPU time? What lines of code allocated objects and started using up memory? Where are your CPU cache misses coming from? They can be more esoteric or fine-grained, narrow things you're profiling as well. But CPU time is the most kind of obvious and common form of profiling. Profiling is great because it's automatic. So once you know how to profile a JVM app, you don't necessarily need to have custom instrumentation or modification of your application to have it profiled. It can be really cheap. So again, cheap here means low overhead, but often it isn't. If you just take something like JVisualVM, hook it up to a production system, switch the profiler on, it will slow your system down quite a bit. We're not saying to do that, but it can be cheap if it's done in the right way and done well. And I'm going to look a little bit later on in the talk as to what makes profilers good for production, what makes them accurate, and what makes them fast. So another aspect where profiling can be more useful over instrumentation is that when you instrument things within your system, you need to know a priori, ahead of time, what bits of your system to instrument. There's a blindness to it, like assumptions that you're making about the way your system works. So we had a customer who had a problem. They were using a commonly used APM tool on their system. And every 5 seconds, they had an HTTP endpoint, and it would be really, really slow. They looked at the APM tool, what its instrument told them about the performance, and their APM tool said, huh, slow? What are you talking about? Your system is working perfectly fine. But when they went to the web page, they could feel it would be periodically slow if they refreshed the page a few times, and their customers were getting annoyed at it being slow. Now, the problem was that underneath the hood, they were using Tomcat as a web server, and it was expiring a resource cache every few seconds. And when you load the resource, it scans the entire class path in order to find whether new resources existed or what was going on there. So every 5 seconds, it would do a 2-second blocking scan of the entire class path. That's not something that servlet request level instrumentation will see, and it's not something that much instrumentation will be designed to see, but something like a profiler that makes a more hypothesis-free view of the system. It's just like, well, what CPU time are we using? Not looking at instrumenting specific things. It can see those kind of problems. And in fact, they used our profiler at Opsian and found the problem very rapidly and fixed it. The other problem, as I say, with instrumentation is you want your system to be flying through the air very, very fast. But in practice, the more instrumentation you add to it, the more time it spends measuring and monitoring itself, and the less time it spends doing what it's supposed to be doing. Performing its business logic, responding to your users' queries, keeping people happy. And that can slow its performance down when what you really want to do is help speed the performance up. So we've always thought, surely there's a better way. Metrics are really useful, really great, but they don't necessarily provide actionable insights. They don't necessarily tell you what bit of the code you need to look at or what bit of the code you need to fix. How about combining profiling in production with metrics in order to understand production systems better? And that's kind of what we do at Opsian. So if you want to have a profiler that works continuously in production, how does that work? I've already said you can't just attach something like JVisual VM to production. What makes profilers that are designed to work in production fast? What makes them accurate and low overhead? Well, firstly, I'm talking about continuous profilers. How would we use continuous profilers? What's the workflow for continuous profilers? Well, looking at a relevant time period and applications or machines where you have a performance problem, you have slow queries, unhappy users, something like that. Choosing a type of CPU profile. So profilers can measure different things like CPU time, wall clock time, memory. We'll look at the difference between CPU and wall clock in a second. Look at the results to find the dominant consumer of the resource. So that's like, what is the biggest bottleneck in your system that the profile is telling you? Fix that, deploy and iterate rapidly. Now, the temptation is often to try and fix as many problems as you possibly can in one iteration. It's often best to try and just fix the biggest bottleneck, keep things simple, because fixing bottlenecks can move and shift the bottleneck around. I mentioned CPU time and wall clock time. Now, what's the difference between these two forms of time? Isn't time just time? Well, the way I like to think about it is in the form of a coffee analogy. So if you're going to a good coffee shop or even a Starbucks at lunchtime, you'll see a big queue of people at the front of the coffee shop. And though people will be standing in the queue waiting to be served, the barista will make them a coffee, charge them some money and give it to them at the end, and then they'll walk off with it. And the CPU time in your system is a bit like the time the barista spends making the coffee and taking your money. And the wall clock time is a bit like the overall beginning to end time within that system. So a CPU time profiler tells you what methods in your system used up the actual time on CPU actually executing instructions. The wall clock time is the beginning to end time. So that can include time where your methods are sat blocked on locks, when they're sat blocked waiting for data back from external processes, when they're waiting for data from disk, doing all sorts of non-CPU things as well. And cutting down non-CPU bottlenecks can often be as big an issue as CPU time problems. If you're going to understand your performance problems through profiling, you really need to see both the CPU time data and the wall clock time data. So CPU time data lets you solve problems like computationally expensive hotspots or inefficient algorithms, bits of code which you think should be nice and fast within your system, but actually they're doing something really complicated, taking up loads of time, operating very frequently. They're also quite good at spotting code that you don't think is executing in your system, but actually is. So something that we occasionally see in people's profiling data, and we look at these kind of systems at Opsian, is they'll have a bit of their system where they're throwing an exception and they're catching an exception. And that's happening a lot within their system. They don't necessarily spot it from just looking at the code because it like gets thrown and caught and not logged anywhere. But it's often the kind of thing that can pop up in a CPU profiler. I'm not saying a CPU profiler is an alternative to a debugger, but it certainly often gives you insights into things about your system where you have to pause and say, why is it operating like this? It shouldn't really be working like that. That's a problem that we need to fix. Then there's wall clock time. So wall clock time helps you diagnose problems where you're blocking the execution of CPU usage. So blocking on what are locks, external I/O, and lock contention issues. So if you've got a modern microservices-based architecture that spends lots of time talking to external systems, doing network calls, wall clock time's invaluable because it tells you, look, you're often talking to this external system through this path in your code base. And if you do things like load up data from disk in order to analyze it, wall clock time, again, can be super useful for profiling and understanding where those performance problems are. Coming to kind of views of data that we get out of profilers. First, there is hotspot profiling views. So a hotspot view, or a flat view as it's sometimes called, is basically just a list of all the methods in your application, ordered by what is using up the most amount of time. Good hotspot profiling views can also give you things like what lines within that view are hot, what lines execute lots of code. Good hotspot views can also tell you things like what stack traces were being called frequently when you got that method executed. So hotspot views are like a bottom-up view of what's going on with your system, from individual leaf nodes that are taking up time to tell you what's important. And when you see a hotspot view looking at things which are high up on the hotspot view, that's the really important thing that you want to look at. A more modern, exciting visualization for profiling data are flame graphs. So flame graphs come in either bottom-up or top-down versions. This is a top-down version. Top-down versions are sometimes called icicle graphs as well. And the idea is that so in this top-down view, for example, the top method here is the top method in your stack trace, so javalang thread.run. And as you go down, there are methods that method is calling. So every layer lower in the flame graph is being called by its parent. And the width of the box, each box represents one method, and the width of the box tells you the time taken up by that method and all of its children. So if you want to see the interesting points on flame graphs, they're points in time where you see the flame graph narrowing down, narrow boxes inside wide boxes, because that means the wide box has a lot of self-time. And flame graphs are a good visualization because they show you what is taking up time in context, what stack traces cause you to get to a different method, what was calling what when things were taking up time and slow. Now, the oldest type of profiler that we have within systems are instrumenting profilers. So if you just run JVisual VM's profiler tab, that's what you'll get. Instrumenting profilers, even though they're the oldest type of profiler, are honestly quite a bad approach to implementing profilers. They're inaccurate, so they modify the behavior of the program because they add instrumentation code into every method within your program in order to measure its time. That means that methods which are small, and so the instrumenting code has a fixed amount of overhead per method, and methods that are small and fast but called a lot have proportionally more overhead to them added by the instrumenting profiler than big methods where they just take the time at the beginning and end of the method. So they can be a bit inaccurate in that sense by modifying the behavior. And the big problem if you want to do profiling in production is that they are slow. Instrumenting profilers can make your system 2 times slower than they normally operate. That sounds high, but if you just think about how many methods within a Java application are things like getters and setters, where it's just reading a field value or writing a field value, and an instrumenting profiler has to add the time and measure the overhead for that time of that getter and setter, you can easily see why the overhead becomes so high. And also, in higher overhead on well-organized, nice Java code that's idiomatically written with lots of small, readable methods. The more readable your code is, the worse an instrumenting profiler's overhead tends to be. Then there's sampling or statistical profilers. So sampling profilers periodically interrupt the threads within your system, and they sample the stack at that point in time. So they say, what's running on this thread now? This is an example little application of flow here. We've got a web server that's running, controllers doing something. We're reading a person out of a repository, instantiating a constructor, doing a few different things. These boxes here are question marks because obviously if you have an infrequently used method, it won't show up in your profiler necessarily. The green arrows coming down here are to indicate the periods in time which you sampled the stack trace. So first sample, second sample, third sample, etc. When you take all of those samples, you can aggregate the data that comes out of them and build views like the hotspots view or the flame graph view that we talked about before. Now, sampling profilers can be really good if they're implemented the right way. But actually, a lot of profiles in the JVM ecosystem are implemented in a not terribly good way. And we're going to talk about how that leads to biases within the sampling mechanism. In order to explain what those biases are, I need to introduce the concept here of a safe point. So a safe point is basically an internal JVM technique used to bring application threads to a halt. So JVMs want to perform JVM operations. Oh, excuse me a sec there. For example, running a garbage collector, doing lots of different things, sampling the stack, for example. And safe points are a way of bringing that application code to a halt and allowing a VM operation within the JVM to run. Safe point polls get added to compiled code periodically. So there's various points in the application where safe point polls are added, beginning and end of methods, back edges of loops, things like that. That poll is basically an attempt to read a specific page of memory. Just read a single value out of that page of memory. And that page of memory can have a protection handler added to it by the VM. And when somebody tries to read some memory out of it, the operating system then bootstraps into JVM code that runs and does whatever it wants and effectively suspends the thread. So that's how safe points work under the hood. In more recent JVM versions, they've been kind of modified so you can get per thread safe points rather than global stop the world mechanisms. But in older JVM versions, including Java 8, the most commonly used Java version, they're a global stop the world safe point. Now, this causes bias when you try and have a sampling profiler, because most of the older JVM profilers use JVM-TI methods under the hood that only profile and measure the stack at a safe point in time. So different green sample points here where we tempted to take them only actually poll the system and only actually sample the thread when we hit a safe point. So for example, in this method, we tried to sample it twice. We would have sampled it twice if we didn't have any bias, but actually those sample points only got called when the next safe point was hit. So it only had one sample in our profiling data. And that is safe point bias. It's times when you should sample a method more often, but because it's not at a safe point, you don't sample it then, and it makes your numbers inaccurate. But it gets worse than that. The JVM performs a series of different optimizations on its code that remove safe points as well. Inlining is an extensively heavily used JVM optimization that makes your system faster. And when small methods are inline inside the JVM, the safe point polls within those methods are removed. And removing that safe point poll is one of the reasons why inlining does speed software up. And inlining lots of methods, as this diagram here shows, all those little green lines being reallocated to the red dot at the end of the method, can sometimes remove incredibly commonly used methods within your system from a profiling data whatsoever and just reallocate their time to the method that was calling them. Inlining can have a big effect. Another effect is loops. The back edges of loops have safe point polls in, but for counted integer loops, so when you've got something that's like for int I equals 0, I less than n, I plus plus, the safe point polls can get removed as an optimization. And then instead of you doing potentially thousands of safe point polls inside a loop, you can do none at all. And that can cause other kinds of biases for computationally heavy loop intensive code. I've run profilers on Java benchmarks that are basically just main methods before, doing a few loops, and they don't know what's going on at all because sometimes those profiling, or like all of their safe point polls, just get removed and they'll get very, very few successful samples. You can see how much time was spent doing save point polls using this print save point statistics flag. And another aspect that that shows as well with the system is the time to save point problem. So when you have especially older versions of the JVM that only have a global save pointing mechanism rather than a per thread save pointing mechanism, all of the threads have to come to a halt. So if you've got some threads going on, like this little fella here, who don't have a save point poll for a while, like maybe they're running some hot for loop, maybe they're calling out to other code elsewhere that doesn't have a save point in, those block your system getting to a save point, and repeatedly doing save point inducing VM operations like bad sampling profilers do means you get a lot of these threads sitting around waiting in time to save points. That can be a problem that really slows down the throughput of your system and adds latency to it as well. So this accounts for a lot of the overhead that sampling profilers can add to a system. But don't worry, I've talked about all the negatives. I wouldn't be talking about it if there weren't some positives as well. If you do statistical profiling the right way in Java, you can do it in a very low overhead manner. So the JVMTI get all stack traces method, which does a VM operation, all those save point polls and all the bad stuff that we just talked about, is too expensive to do frequently. But what we actually want to do in order to profile data is interrupt an application that's running and sample the resource of interest. So see what the stack trace is doing. And we can do that with what we call advanced statistical profiling in Java. Operating systems, at least Linux and Mac OS, have the ability to interrupt the system that's running with operating system signals. There's a signal called sigprof. So if you're used to doing things like kill-9 to a process to force it to quit on your system, that is sending signal number 9 to the process in order to interrupt it. But sigprof is just another signal number, and instead of that killing the process, it gets delivered to a handler on one of the threads within that process. It's very lightweight, very low overhead, and a very efficient. There's no more efficient way of interrupting that process than using the operating system's signal handling measure. If you want to reduce the overhead even further, you just sample with lower interval frequencies and rely on the fact that you're always sampling in production in order to gather the number of samples and stack traces to understand what's going on. The JVM itself has a method in it called async get call trace that lets you read the sample stack. It says async here, and that means it's async safe. So it's something that can be called within a signal handler. There are limitations of things that you can do within signal handlers in order to read data. So you can't call malloc, for example. That's not an async safe method. It can't be, it's not reentrant. You can also examine the JVM internals if you want to read other things about what's going on, for example, the state of the thread. Now, advanced statistical profiling isn't used by certain desktop commercial profilers. It isn't used by JVisual VM traditionally, but it can give really, really low overheads in terms of profiling. Like, we have people who use this kind of approach in production all the time with less than 1% overhead for sampling rates that give them useful data that they can reason about their system with. So it's really great. Now, there are low overhead open source profilers like Async Profiler, Honest Profiler, Java Flight Recorder in certain JVMs now is open source in newer versions. There's also backports of Flight Recorder to 8. And there's also the Solaris Studio Profiler as well. So these are what we call low overhead ad hoc production profilers. So they're low overhead enough for you to use them, but they're still ad hoc in the sense of you having to connect them up to production. But people in practice, when they're trying to do continuous profiling in production, they're put off by practical issues as much as they are by technical issues. So the first barrier that we see to people doing production profiling in an ad hoc manner is it requires access to production. This is a picture of the good old Thames barrier that's stopping us from being flooded in London on the right. So what does that mean? Well, so many people don't have the ability to do things like SSH into a production server, connect in, run an ad hoc profiler, and then leave. That's considered high risk work, especially when you might have a performance problem induced outage that's going on at something and you don't want to break the system further. It can also be a big problem for certain organizations where you have things like internal Chinese walls in finance, in banking, where people who write code are not allowed to be people who have production access as well. It also requires manual work. Like if you've got a performance problem in production, you just want to see what the solution is. You don't want to have to do some complicated, risky SSHing in and connecting up a profile a step. You just want something that's always connected. And if we profile all the time, not only do we overcome that barrier, that impediment to doing it when we have a performance problem, we gain other benefits as well. Firstly, historical data. If you have a performance problem that happened, say, last night at 1 a.m. when your development team was asleep, or dealing with their crying baby at home, or whatever it is, then it's difficult to do an ad hoc profiling investigation at that point in time to connect up to your system. But if you've just been profiling the system all the time, you can log into your dashboard, say, look, what happened at 1 a.m. last night? You can see what the data is going on there. You can correlate that with other data and metrics that are going on in the system. And if you have an intermittent problem, you can see, look, every time we saw this thing in our profiling data, we also saw these other metrics go up at the same time. So that's very useful. It also allows regression analysis. So you release a new version of your software to production, you can see the performance data before and after when you've got historical data. Very useful. Putting samples in a context. If you've got a continuous profiling system that gathers things like the application version that you're using, the type of machine if you're running on a heterogeneous environment like AWS, locations, things like this, you can look at profiling data and slice and dice it. Why did this machine have a problem and that machine not have a problem? You can't do this very easily with ad hoc profiling because it's all ad hoc, isn't it? It's not methodical. It doesn't gather all this other data that you can use to compare between different systems. This is not just an approach that we do at Opsian. There's a paper that Google published a while ago called Google-wide profiling that talks about continuous profiling. Very interesting, worth a read, something they've been doing actively at Google and found very useful for a while. I'm not someone who advocates software developers just copying techniques that work at Google, because Google are a big company. We shouldn't just blindly copy things, but there are definitely lessons that we can learn from things that they're doing well, and I think continuous profiling is one of them. How do we think about doing that continuous profiling? Well, the way many services should work for gathering this kind of data, and the way Opsian, our service, works is we have some JVM agents. They run inside people's JVM processes. They send that data back to a common aggregation service, and then you can look at that data in just a web-based report. That means that different members of your team that could be located in different offices around the world, or especially nowadays remotely in their own homes, can see that same data from that same web report that makes it easy for them to make comparisons with, rather than just looking at, say, the profiling data on a command line or a single person's GUI as the traditional desktop profiling UI gives us. The aggregation service also means that you can compare profiling data from different JVMs, different systems, things like that as well. So in summary, it's possible to profile in production with low overhead. It's possible to profile really accurately in production. But there's also the practical issues for production profiling as well. It's not just about being low overhead and having a clever way of sampling. It's about doing it in a way that's practical for people. And we gain new capabilities by profiling all the time, like the historical data or the ability to compare things. So to just kind of wrap up this talk and conclude, we should firstly give some thanks to people who've done loads of work in the low overhead production profiling space. So Brendan Gregg was a guy who came up with the idea of flame graphs. He works at Netflix. Very cool idea there. Andre Pangin, who's recently become a Java champion, actually, just to mention Java Champions Conference, doing great work on async profiler, during Mountain works at Google, open source and lightweight profiler code, very influential. Johannes Rudolph worked on an alternative profiler that mapped Java and the Linux perf tool together. Nitson, another Java champion, has also contributed to some of these projects. And obviously the people who worked on Java Mission Control and Flight Record and the Solaris Studio teams as well have all done good work on kind of pushing forward the state of the art and the state of the practice as goes with profiling in the Java ecosystem. So we talked about a few things in this talk. Firstly, we said performance matters to your business, and where it matters most is in a production environment. Solving those unknown unknowns, things that you didn't think about happening, things that you wouldn't have thought about happening ahead of time, that's where the tooling really matters, where it really helps you. Development and production are different. They're different in terms of hardware, they're different in terms of software, they're different in terms of the load test that you're running. Your performance tests are really, really hard to make realistic compared to your production data. And your production data is the real data because it's production. Metrics can be very useful for understanding where problems are. You CPU bottleneck, you IO bottleneck, different things like that. But it's difficult to just look at some metrics and see exactly what bit of your code to change. They can be difficult to immediately action. And that's what we want. We want actionable insights. We want to see a problem, fix a problem, everyone's happy. Instrumentation, very, very high level of granularity and detail about what a production system is doing, but also quite high overhead. And the more fine-grained you instrument your system, the higher the overhead. Continuous profiling can provide that actionable insight, can provide that useful data. But to do continuous profiling, you need to both have a low overhead way of measuring the system that isn't going to slow your production system down, and also this kind of framework and ecosystem for gathering that data as well. So we think that we kind of need a real attitude shift on profiling and monitoring in general. So there's different parts of that. Firstly, being systematic, not ad hoc in terms of the way you approach things. So instead of trying to just see a problem and whip up an ad hoc solution, what are the systematic approaches and processes we can do for measuring production systems, finding and fixing performance problems, for understanding how systems behave? Systematic in the sense of I can apply them repeatedly time and time again, and I can understand what's going on. Be a bit more scientific with what's going on there, and a bit less artisan. Being proactive, not reactive. So that doesn't necessarily mean going off and doing premature optimization on software systems. That means putting in place the tooling, the infrastructure, the monitoring, the observability to understand what's going on in that production system, rather than only reacting and going from one tire fire to the next or things like that, which I've seen a lot of teams unfortunately do. Whereas if you get a firm foundation, if you're proactive with these things, you get systems that perform well and can be easily monitored and measured and are high performing. And underlying that is being continuous, always being measuring things in production, always be deploying to production, always be having a short feedback loop about that data that you get from production in terms of monitoring, in terms of profiling, in terms of even things like logging, whatever it is, get a short feedback loop so you can understand what your production system is doing. In short, please do production profiling all the time. That's the kind of one sentence takeaway from this talk. And I run a business called Opsian with my co-founder Sadiq, some other people, and we do have a continuous profiling tool as well that you can get a free trial of from our website. So if you're interested, go check it out. Some of our customers have described it as being like a magnifying glass for their servers, but we are more interested in people doing this and getting better at measuring their systems than any particular tool. So I don't want to turn this into a hardcore product pitch. I just thought I'd mention our tool in there as well. And that's the end of the talk. So a great time to bring Henri back in and ask if there are any questions.
Here I am.
Hello.
There's a lot of questions actually, and a lot of love in the comments. Chandra is probably your number one fan, your number one fan, and he has a lot of meaningful questions. So, first one is, how about the effect of C1 and C2 caches during instrumentation?
How the effect of C1 and C2 caches during instrumentation. So for people who aren't familiar out there, C1 and C2 are the different compiler tiers that you have within the hotspot JVM. As to how instrumentation impacts that, it's hard to tell on a system-by-system basis. But basically, instrumentation, it's always adding more code to the system under operation. It's always taking time away from your system operating, regardless of whether you're using a client or a server JIT. So it's always eating up more space inside the code cache, inside the JVM. If that's what he's focused on, that's definitely correct. And it's also reducing the likelihood of methods being inline, because inline thresholds are often based upon whether methods are small or not. So by instrumenting more code, you reduce the probability of inlining and make performance worse.
Great. Then a follow-up, what do you think about the perf tool on servers?
The what tool on servers?
Perf, the command line PREF.
I think perf is an interesting library and an interesting ecosystem. We use perf data actually within Opsian as well. But perf as a command line tool, I don't think it works very well in terms of the scalability, right? Like you've got 100 systems in production. Do you want to SSH into all of those systems and run perf on them individually? That's difficult. And it doesn't, it's like a useful low overhead tool, but you need like a framework and an ecosystem to scale it and implement it within your system, within your software system and business.
Thank you. I do use it with JMH a lot, but on servers it's harder.
Yeah, it's good. It's definitely good with things like micro benchmarks and stuff like that.
So the question was from Michael. Now some more Chandra questions. Does using no GC such as epsilon help during instrumentation?
I don't really think that epsilon GC has any influence on the instrumentation that an APM tool would perform. I don't think. Epsilon GC, again, it could be a useful tool in a micro benchmark for eliminating the noise from doing a GC run, but probably not something that many people are going to run in production.
Yes, indeed. Then we have how does save point logic work for cyclical complexity recursive calls and tail recursive calls? Ooh.
How does save point logic work for
I don't know why cyclical complexity, but recursive call and tail recursive call you can.
I mean, with a general recursive call, you've just got your, when you do a method, you've got your poll at the beginning and a poll at the end of the method. So if you're making a call to another method, you've got a poll at the beginning and a poll at the end of the method. That's not affected by recursion as such. Tail recursion, I'm not sure what the JVM does in terms of tail recursion. Last time I investigated this area, it's a few years ago, I admit, but there was no particular optimization being done there. So I don't think it has any I don't think the tail recursion or the recursion has any other impact on safe points beyond, safe point, beyond the regular safe point polls, to the best of my knowledge.
Yeah, from as far as I know, there's no tail recursion optimization. So I think, that's fair. What is your, so that's from Michael again. What is your favorite profiler and why? Sorry, just curious.
So yeah, as I say, I run a business called Opsian. We've got a continuous profiler. It's hard for that not to be my favorite profiler, because it's the one I use all the time and profile with. It's a bit of a biased answer, but I can't really say anything else, to be honest. I really do like the work that Andre Pangin's done on async profiler, though. I think for like a development profiler, something to use, and also I know IntelliJ have added support for that as well. So I think that's also a really nice tool to use.
Sounds fair. What about using JFRs? Those are supposed to have the lower cost since it's integrated in the JDK. This is from Juan Pablo.
Yeah, so I mean, JFR is definitely a very good tool. I put it on that list of low overhead profiling tools. I think it's one of those things where in order to make JFR work, it's not just about using JFR. You have to use like an APM tool or something that feeds data into as well, rather than just it on its own. Mission control, again, desktop profiler, can be quite good. The only thing I would say with JFR is, and I know some of the people, especially the people at Datadog, were working on improving this, but I have had several times with JFR and mission control where I've tested it out in environments before, and it's given me quite inaccurate profiling results. And that was basically as a result of the way that they historically, I mean, there's still their default profiling event does a bit of a weird sampling system. I'm not sure I can accurately describe it off the top of my head, but it like picks a series of different threads and round robins them. It doesn't do the same things a SIGProf profiler would do, and it doesn't just do straight round robining either. I've found that to result in very inaccurate results when you have, I mean, the worst one was when I was trying to profile an open source project that I maintain called RTO that has one thread that's doing lots and lots of work and is very active, and it was just not getting many samples. So I do think it's good, but you have to be a bit careful. I know I talked to Marcus Hurt a while ago, and he said he was definitely improving the CPU. They were getting a proper CPU time and proper wall clock time profiling events, but some of the older ones can result in inaccurate data.
Ah, that's good to know. Great. And now we have, how far can you use JITWatch in production?
How far can you use JITWatch in production? So JITWatch takes in a log of JIT compilation events and tells you what's going on. So you can just turn that JIT compilation log on. It's pretty low overhead, to be honest. So I think that is sort of viable from an overhead point of view. But then the question is, can you again, does it scale to lots and lots of different servers, or is it one of those things where you've got to like pull a log back in from the different servers and things like that? And also, JITWatch I think is quite useful, but only when you've really tuned the system already and you're kind of like, what's going on here? Why isn't this inlining or something like that? It's a very useful tool, but it's like it's a real scalpel type tool, you know.
Really low level. I think that's the last one. Yes, the last one was, how does Option compare to your kit? And my answer would be, it's a production profiler. Your kit is not. That's the start.
Yeah. that's the difference. We're like, you know, 1% generally for organizations overhead continuously switched on. So you can just run us in production all the time. And I don't think people generally do that with your kit.
Not recommend. I won't. Not sure I would do that. No. I'd be really afraid. I think that's it. I'm sure the question. Thanks for the answers.
Great.
Thank you very much for being with us.
Thanks for having me. I'm looking forward to seeing some of the other talks at Java Champions Conference as well over the next few days. But yeah.
Oh yeah, I need to. Where do I have that? Okay, I'll post the next presentation in the comments, which is somewhere by there. Let me see, and then we'll close. We'll close it up. Thank you very much for attending, and see you in the next talk. And broadcast if I can, and